Good morning, everybody. This is lesson 6.2, mechanical wave and light wave phenomena. Obviously, if I was in class with you, I would be teaching this live, but unfortunately, I cannot do that. So here I am teaching you via video. Okay? If you have any questions at all, obviously you can send me an email and I will get back to you as soon as I can. So let's talk about mechanical wave phenomena. So the first thing that we're going to talk about are called beat frequencies. These are steady beats produced when two closely matched frequencies are happening due to constructive and destructive interference. Okay, the next one is resonance. This is when a vibration of a body at its natural frequency is caused by an external vibration also produced at the same frequency. So you've probably heard that word resonance before. So where we commonly see this is if an opera singer is singing very high, she can shatter glass or he can shatter glass. That's actually called resonance, right? So what happens is they are creating a wave at this certain vibration. And the glass, or whatever, like a wine glass or a mirror or something, is vibrating at a very particular frequency. If they match that frequency, that is causing the vibrations to happen a lot, right? Very frequently. And after a while, the material cannot take the stress and it shatters. Okay? So, again, this is kind of what I just talked about natural frequency. It's just this very specific frequency at which an object can vibrate if disturbed. Okay? So, some examples swings, pendulum, the Tacoma Narrows Bridge, tuning forks, MRIs. Like I just said, if you have an opera singer, you will obviously see them shatter glass. Okay. If you recall, this is the bridge that we looked at in the beginning of the year. I also showed this to you when you built your bridges, right? Bridges should not be able to move kind of like in waves. Like we shouldn't be able to see those peaks and valleys, peaks and valleys. That's very dangerous, obviously. And this bridge eventually did collapse. And the reason why it collapsed was because the wind, due to the Tacoma Narrows, right, where it's located, the wind produced a certain vibration that matched that bridge's natural frequency. And so the bridge started to oscillate or propagate, right? And you have concrete that's oscillating up and down where it shouldn't be doing that. And after a while, the bridge was unable to hold that amount of stress and simply collapsed, like the roadway collapsed, okay? And the towers just stood. But today they have rebuilt that bridge, okay? You have MRIs, which is what you go in if you're in the hospital or something like that. And then a tuning fork, um, they look like this. I know they kind of look weird, but it's kind of like a xylophone. So basically you have a mallet and you hit the tuning fork and you can hear it like make its special sound. You can also hit a tuning fork, and you can bring a very closely related tuning fork, right? Because they're all different frequencies. So if you take, two different notes, but they are fairly close to each other and you hit it, one of them, and you bring it near it, you'll actually create the vibrations, and that other one that you didn't hit will start to vibrate, and you'll actually hear it in your ear. It's actually a really cool thing to witness. All right, so the next mechanical wave phenomenon that we're going to talk about is known as a standing wave. So a standing wave is just the appearance of a stationary wave. So stationary means still, right? It doesn't move. So it appears like it's staying still. Okay, it's not moving. How this standing wave forms is when two waves of the same frequency and amplitude are traveling in opposite directions within the same medium. Okay, so if you look at this example right here, the red one is moving this way, and then the blue one is moving in the opposite way. And if you take notice to the black one, right, where there are points where they kind of come together, they're constructive interference, it simply gets bigger and then it decreases, right? So it's kind of like this flip-flop back and forth. It appears like a stationary wave, but it's not. It's actually really moving, okay? And then we have this idea of nodes and antinodes. So what a node is, it's where there's zero displacement due to destructive interference. We learned that destructive, right? This word destructs means to get smaller, right? So we definitely shouldn't be getting bigger. So if we get smaller, it makes sense that we're going to have zero displacement, okay? And an antinode, right, where it's maximum displacement due to constructive, we know this gets bigger, okay? So we kind of use our knowledge of what those words already mean, and we see it in the following diagram, okay? So, right, we said a node should get smaller, so actually let me change the color. So this bright green is going to represent the equilibrium line, So my node right here is on that equilibrium line. I have a node right here also on the equilibrium line, and I have another node also on the equilibrium line, okay? That's because there's zero displacement happening at that position, whereas my antinodes, they are actually happening at my crest and my trough, okay? So your peaks and valleys, also known for us as the crest, which is the top part of the wave, and the trough, which is the bottom part, those are where my antinodes come from because those represent maximum displacement from that equilibrium position. Okay, should make sense because if we're having constructive interference, we are going to get bigger. Okay, so knowing that information now, let's do a node and antinode example. So the diagram below represents a standing wave. Okay, the number of nodes and antinodes shown in the diagram is, so this is what they want me to find. So what I recommend you do first is actually draw in your equilibrium line. So I'm going to go right through this wave. Whee! Okay, that's my equilibrium line. So that dotted line, what they're saying, that's not the actual wave. The wave is the solid line. Okay, so this is the actual wave, the solid one. Okay, because they have to tell you it's a standing wave, you'll see this. So this is your standing wave. Okay. That's how they're going to verify it with a picture. It's kind of hard to show you in 2 dimensions instead of like, if it's a moving animation, but this is exactly what a standing wave will look like in a diagram. So now that we drew our equilibrium line, based on what we know about nodes and antinodes, let's start with the nodes. Nodes is where we have no displacement from the equilibrium line. So I start right here. I'm at 0. I'm at 0 over here. I'm at 0 over here. 0, 0, and 0. So in total, the number of nodes equals 1, 2, 3, 4, 5, 6. Okay, so I have 6 nodes. Again, that's because I have 0 displacement. Then I have 1, 2, 3, 4, 5. Again, we are only counting the actual wave. Okay, so that's the solid line. All right, so I'm going to write that on top. Solid line. Okay, that's the only one you're going to count from. So we counted 1, 2, 3, 4, 5. How do we know that's antinodes? Well, they have the maximum displacement at either the crest or the trough. Okay, so our antinodes equals 5. So we can get rid of choice B. We can get rid of choice A. Choice D makes no sense because where this 10 antinodes comes from is because they counted 5 on the solid line and 5 on the dotted line. And like I said, the dotted line is not the actual wave. So the answer is this. Okay, so pretty straightforward and simple. Another example, while playing, 2 children create a standing wave in a rope, as shown in the diagram. A third child participates by jumping the rope. What is the wavelength of this standing wave? Okay, so this is kind of a little bit of relation back to Algebra 2, what you guys learned about a wave. Okay, so take note to what you have here. So again, the solid line is your actual wave. Okay, so keep that in mind. And then your dotted line is, that's just a representation of, hey, this is a standing wave, okay? So take note, you only have the trough. You only have the trough part. And you know that one full wavelength is uh, a trough to a trough or a crest to a crest. Okay, so there's an issue right here. Okay, so that means that my cycle has not been completed. I'm missing a part of my wave, right? So I only have this part. So then technically I would need to have a crest, right? And so I will continue the dotted line that they gave you in the picture to still represent my standing wave. So what that means, right? So now I have from over here to over here. That's one cycle of my wave. So in order for me to find the full wavelength, I have to take this value of 4.3 meters, and I have to add another 4.3 meters because this distance right here is the same amount because I needed to extend my wave. So I was given a crest, I was given a trough and I needed a crest as well. Okay, so I just drew them in. And this is the same thing you do in algebra 2 when you have a graph that goes to pi. You need to understand that that graph actually goes to 2 pi because you're looking particularly at circles, about how sine and cosine work in circles. So you need to do the full 360 degrees. Okay, so likewise, that kind of follows through with us. So the answer that you should get is actually, oops, I just wrote plus sign. You should get, oh, what's happening? No, okay, there we go. 8.6 meters, okay? You're just doubling your initial value of the distance of just from the, like, kid number 1 to kid number 2, okay? You're taking that value and you're just doubling it, okay? So another standing wave example, the diagram below represents a wave moving toward the right side of the page. Okay, so it's going to the right. And then, what is a standing wave? Well, we first learned a standing wave is when you have two waves moving with the same frequency and the same amplitude. So right away we can say, because these have different amplitudes. So these are not going to work. Okay, so same frequency, same amplitudes. But the only thing that is going to be different is that while they are moving in the same medium, one has to be moving this way. So clearly, I can't have a wave that's going to move in the same direction. That's not going to create a standing wave. Okay, so I need something that moves in the opposite direction. And that answer is choice number C. Okay, I have a wave going like this, right? So it's traveling this way. I'm going to erase this arrow right here, and I'm going to draw it with a different color. I need a wave of the same amplitude, just traveling that way, and that's how I get my standing wave. Okay? So that's pretty much it for, like, at least the mechanical wave property. Now we're going to talk a little bit more specifically about other types of phenomena we see.